Welcome to our talk, Just-in-Time Code Reuse. My name is Luca Davi. I'm a research assistant at the Technical University of Darmstadt. And this is Kevin Snow from the University of North Carolina at Chapel Hill. As you can see from the title slide, the work that we both present today is a collaboration among different co-authors affiliated to one of these universities, namely Alexander Dmitrenko, Christopher Liebchen, and our advisors Fabian Monrose and Ahmad Reza Sadeghi. Today we will present you a novel attack technique that we refer to as just-in-time code reuse or just-in-time return-oriented programming. In general, code reuse attacks are based on the principle of exploiting a software bug such as a buffer overflow error to afterwards induce arbitrary malicious program behavior. And this is achieved without requiring any code injection from the attacker's side. Instead, the attacker reuses existing code pieces called return-oriented programming gadgets that already reside in the address space of the application. However, in the traditional model, the attacker has to run a static and offline analysis phase where he inspects the binaries and libraries to find and identify useful gadgets that he wants to use for his exploit. Now, a potential defense against these attacks is the enforcement of memory randomization, such as ASLR. However, as you all may know, ASLR is vulnerable to memory disclosure attacks, where a single leak pointer is sufficient to still launch code reuse attacks. To tackle this shortcoming, a couple of researchers investigated fine-grained randomization techniques, where you do not only randomize the base address of a code segment, but also the internal structure. And the claim of these proposals is that if you have fine-grained randomization, a single leak pointer is no longer sufficient to launch code reuse attacks. However, as we will show you in the next minutes, our technique is able to bypass these schemes and to reuse the existing memory disclosure vulnerabilities that are already out there to leak a large amount of memory pages and afterwards identify return-oriented programming gadgets on the fly without requiring any static analysis. Before Kevin will walk you through, as the main developer of the attack, will walk you through all the attack details and even show you an exploit against IE10 running on Windows 8 using the latest vulnerability that has been also exploited in the Pawn-to-Own contest this year, I will briefly walk you through the basics of return-oriented programming and memory randomization. The most widely exploited software programs today are very rich reading processing programs as well as web browsers. And typically, these applications have the ability to embed many types of data. And also they feature scripting facilities such as JavaScript, which an attacker can utilize to facilitate his attacks. Moreover, these applications link by default to a large amount of native code, which makes them subject to runtime attacks. Nevertheless, current operating systems deploy the principle of non-executable memory, ensuring that a memory page cannot be writable and executable at the same time, thereby rendering code injection attacks infeasible. Hence, attackers today have to rely on code reuse attack strategies, where they already reuse code pieces that reside in memory and are marked as executable. And a prominent example for code reuse attacks is return-oriented programming. A good analogy for code reuse attacks or return-oriented programming is a newspaper article. Consider this article that consists of a large number of letters that form words and at the end sentences. If we now are able to extract a couple of letters and combine them in a malicious way, we can derive new words that have been never intended by the author of the text. For instance, in this example, we have the new word return-oriented programming. And this is actually the basic idea behind return-oriented programming. One has only to replace the letters with machine instructions, meaning that an attacker can generate new malicious programs out of existing benign programs. A more technical view of the attack is shown on this slide. Consider an adversary and an abstract view of a program memory layout, where we have segments for code, heap, and stack. In the code segment, we have a couple of so-called return-oriented programming gadgets, where each gadget fulfills a particular task, such as loading a word from memory or adding two registers. Another property of all these gadgets is that they terminate in an x86 ret or return instruction. And this instruction is actually giving return-oriented programming its name, as you will see soon. Moreover, in this simplified example, we consider a couple of stack variables, and the stack pointer is currently pointing to the top of the stack. The first step now of the attack is to inject the return-oriented programming payload. However, the payload in this example does not consist of malicious code directly, but of a chain of return addresses where each return address is pointing to one of these gadgets. Moreover, we assume, in this example, a heap vulnerability, which an attacker can exploit to hijack the execution flow of the program. In particular, he redirects the execution flow to the gadget that is pointed to by the first return address. And this return address points to the stack pivot gadget. This gadget has a particular task in every return-oriented programming payload. Specifically, it sets up the stack pointer so that the stack pointer points to the beginning of our return-oriented programming payload, which in this example is return address 2. Once the final return instruction is issued by the stack pivot gadget, then we pop return address 2 from the stack and redirect the execution to the next gadget in our chain, which is the load gadget. And automatically the return instruction advances the stack pointer by 4 bytes. And an attacker can now repeat this procedure as long as he desires. For instance, after the load gadget has been executed, the return instruction would redirect the execution to the final gadget, which is the add gadget in this example. Obviously, code reuse attacks already exist for a couple of years. And to give you a very brief and selected overview of the most relevant papers in the space, we have created this slide. It basically started in 1997, where Solar Designer presented an exploit where he was able to redirect the execution to a library function in libc. In 2001, Nergal advances this idea and showed how to call a chain of functions in a return into libc-like fashion. In 2005, Kramer presented borrowed code chunks exploitation, which already included the basic ideas of return-oriented programming. Specifically, he used a couple of gadgets to load registers to afterwards call functions. In 2007, Hovav Shacham finalized this idea and presented his paper on return-oriented programming. In particular, he showed that the attack technique, in contrast to standard return into libc, is Turing complete, meaning that you can run arbitrary computation and malicious behavior. In 2008, Hovav also presented return-oriented programming on BlackHat. And moreover, in the same year, we have seen return-oriented programming attacks against Spark processors and Atmel AVR embedded processors. In 2009, Ralph Hund et al. Showed that return-oriented programming can be also applied to rootkits. Moreover, in the same year, FX Lindner showed return-oriented programming against Cisco routers, and Charlie Miller and Vincenzo Yuzzu showed an exploit against iOS running on ARM processors. And finally, in 2010, we had a couple of papers at BlackHat, and also return-oriented programming has been used in the Pawn-to-Own contest to exploit the Safari browser on iPhone and to exploit IE8 on Windows 7. Moreover, we also have seen a paper on return-oriented programming without returns, showing that the attack does not necessarily require return instructions to be executed, but indirect jumps and indirect calls can be used as well. However, all the mentioned works require that static analysis phase to identify the gadgets that an attacker wants to leverage in his attack. Now, one potential defense, at least from a theoretical standpoint of view, is to deploy address space layout randomization. The basic idea of ASLR is to randomize the start or base address of code and data segments. Consider for this, again, an abstract view of a program memory layout where we have segments for library, executable, heap, and stack. If the application is restarted, then all the base addresses get randomized, and an attacker can only guess where his gadgets and code that he wants to reuse resides in memory. However, ASLR is vulnerable to memory disclosure attacks, where an attacker retrieves a single runtime address, and based on that runtime address, such as a leaked function pointer, he adjusts all the addresses pointing to his gadgets by the randomization offset. This attack is possible because ASLR only randomizes the start address, but the internal structure remains the same. A more detailed example of a memory disclosure attack is shown on this slide, where the example is taken from Cerna's last year's talk at BlackHat. Consider a couple of objects on the heap, where the first object is a vulnerable object that contains, as a member variable, a buffer. Afterwards, we have a JavaScript string, and finally, an object that contains some interesting function pointers that we want to read. The attack now works as follows. We overflow the buffer and override the length field of the JavaScript string. In particular, we set it to the maximum size, which allows us to use standard string methods in JavaScript to read any address from the memory space. In particular, we can read the function pointer of the object that is just next to the JavaScript string. However, the challenge here is that we can only read from addresses that are mapped to the address space of an application. Otherwise, the application would crash and the exploit would not work. Now, to tackle this shortcoming of address space layout randomization, where a single leak pointer is sufficient to bypass the entire scheme, researchers have proposed in the last 2 years the principle of fine-grained address space layout randomization. And the idea is quite straightforward. We do not only randomize the base address of a library, but we also randomize the internal structure. For instance, in this example, instruction sequence 1 is moved from the top to the middle, and the other instruction sequences, their location are also randomized. Now let us go in more detail for each of these proposals. The first proposal presented by Papas et al. Enforces randomization within a basic block. And the authors specifically propose 3 randomization techniques. The first technique is based on instruction reordering, which is obviously only possible if the instruction sequence, if the instructions have no dependency from each other, so that they can be easily switched. The second technique proposed is instruction substitution, where we replace an existing instruction with an equivalent instruction that has the same effect. Note that this technique does not directly prevent return-oriented programming. However, recall that return-oriented programming can also be based on unintended instruction sequences, where we have a C3 byte representing a return instruction in x86 within the opcode of a move instruction. So to eliminate these unintended instruction sequences, one could deploy this instruction substitution technique. And finally, the authors propose register reallocation. If this is, for instance, possible if a register is free to use, then we can replace that with another register. However, this scheme only performs randomization within a basic block, so that functions remain at their original position, allowing return into libc attacks still to happen where I call entire functions. The second proposal uses basic block randomization or basic block permutation. And the idea is as follows. Consider we have 3 basic blocks in our program, and each basic block consists of 2 instructions, where we have also a call instruction that in BBL1 that calls the BBL3. Now we reshuffle all the BBLs in the memory so that they get a new position. So BBL1 is moved to the bottom, BBL2 to the top, and finally BBL3 to the middle. This reordering also involves adjusting memory addresses. For instance, the former call to the address of 10FF has now to be adjusted to 10A0 because BBL3 has moved its position. Moreover, the return instruction issued in BBL3 will target the instruction following the call instruction in BBL1. Hence, we have to add another jump instruction to preserve the semantic original flow of the program. As you can see, this technique requires a lot of binary rewriting techniques, which is a challenging task. The final randomization technique that I want to present is instruction location randomization technique. This technique offers the highest entropy for randomization. It basically randomizes the location of every instruction in the memory. So if you have an example of 6 instructions, then all these instructions are distributed over the entire memory. And again, we also have to adjust memory offsets. At runtime, the program is loaded into a binary instrumentation framework, and the execution is guided through a so-called false-through map, which indicates which instruction needs to be executed next. And obviously, this entire binary instrumentation framework induces a lot of performance penalties and also uses the benefits of cache models because every instruction is distributed in memory.
All right, so the main question we were trying to answer in the work that we did was whether fine-grained ASLR actually provides any benefit over the standard ASLR scheme. And if it does, we want to know if it is going to provide a viable defense in the long run. So in our pursuit of answering that question, we made the following contributions in our work. First, we developed a novel attack class that does in fact undermine fine-grained ASLR that we dubbed just-in-time code reuse. Second, we also show that memory disclosures are far more damaging than many have previously believed. Finally, we don't just talk about this idea in theory. We actually developed a prototype exploit framework that demonstrates one instantiation of our idea. And since that instantiation is based on the paradigm of return-oriented programming, we call it JIT-ROP. Before I get into the details of how JIT-ROP actually works, let's talk about some assumptions. On the defender side, or the vulnerable application that we're trying to protect, we assume a non-executable stack and heap. And this essentially means that the adversary is not able to directly inject code to execute as a payload. Instead, they have to make use of some code reuse strategy. Second, we also assume a strong fine-grained ASLR scheme is used with no implementation-specific flaws. Think about all the fine-grained ASLR schemes that Luca just presented, combined and just taking the best features of all those with none of the problems. On the adversary side, we have similar assumptions to those that are required to defeat standard ASLR. Namely, we do require that there is a memory disclosure vulnerability present that's going to enable us to read the value of an arbitrary address in memory. Second, we also require that there is some control flow vulnerability that's going to allow the adversary to redirect the normal control flow of the program to whatever payload we're able to generate. Now in practice, this control flow and memory disclosure vulnerability are often actually the exact same vulnerability, just exercised in a different way to achieve these two different goals. So here's the basics of the workflow of our JIT-ROP framework. First, the adversary needs to do a few things manually. Just as they would need to do to defeat standard ASLR, the adversary is going to have to leak a code pointer. And they can do that using the memory disclosure vulnerability that we assume is present. Second, the adversary needs to provide some sort of exploit description that's going to be written in a high-level language that we created. And that exploit description is just telling us what the adversary wants the actions to be taken after the exploit completes. Finally, keep in mind that all the steps I'm going to talk about are all happening at runtime within the context of a vulnerable application that's making use of a fine-grained ASLR scheme. And because fine-grained ASLR is in use, we know that just leaking a single code pointer is actually not going to give us any additional useful information that's going to directly help us to generate a ROP payload. So the first thing the JIT-ROP framework takes care of for us is, given a single initial leaked code pointer, the JIT-ROP framework will try to map as many pages of memory as it possibly can. And I'll get into the details of how we do that in a few slides. Next, because fine-grained ASLR is in use, we don't know any useful information about pre-existing code sequences that we can use as ROP gadgets. We have to discover all that dynamically at runtime. And so that's the next step that JIT-ROP takes care of automatically for us. Next, because any useful payload that an adversary might want to run does eventually need to interact with the operating system, and the canonical way of doing that is through API calls, we're going to need to search for the API calls that the adversary requires in their exploit description and provide those back to them. Finally, we take all the information that we collected in all of these steps, as well as the adversary's exploit description, which is just this high-level language, and we dynamically compile a ROP payload based on all the information we found. Then we return that ROP payload back to the adversary's script, and The adversary can then leverage the control flow vulnerability to redirect the program control flow to the newly generated ROT payload. So I know that all looks very easy in our high-level diagram there, but we actually had encountered a number of challenges along the way. And the biggest one, in my mind, is that we have to find a way to map memory without crashing the program. Although we do have a memory disclosure vulnerability available that allows us to read the value at an arbitrary address, it turns out that, at least in all the applications we looked at, over 90% of the memory space of the program is actually unmapped. And if we use the memory disclosure vulnerability to read one of those addresses, the program's going to crash and our exploit is going to fail. So we needed to find a way to reliably do this without crashing the program. Second, keep in mind that we have no prior knowledge. Ahead of time, we do no static analysis to determine what ROT gadgets are available, because fine-grained ASLR is going to change all that each time the program runs. So we have to be able to find all the gadgets we need, find all the API calls we need, and use all that information to compile a payload all completely dynamically at the time the exploit is running on the victim's machine. And because this all has to be done at runtime, the entire process needs to be fully automated. There's no room whatsoever for error. The adversary can't step in and manually fix anything along the way, because by the time this is all running, it's already on the victim's machine. Finally, as I mentioned before, we don't want to just talk about all this. We actually want to see if we could build this framework and demonstrate that we can provide an efficient and practical exploit. So here's how we address some of those challenges. First, for mapping memory, we made the observation that if we can leak just this single function pointer, that actually tells us that there is at least a whole page of memory present. And that's just virtual memory, how virtual memory works. And if we know a page of memory is present, since memory pages are aligned in memory, we also know exactly where that page of memory starts and where it ends. So when we have that information, we can leverage the memory disclosure vulnerability to leak the content of that memory page. Then again, at runtime, we disassemble the contents of that code page, and we look for all call and jump instructions that point to another page in memory. When we find those, we queue them up and perform the same analysis on those, and we recursively repeat this process until we've exhausted all the pages that are somehow interconnected with that initial leaked function pointer page. Now that we have all the pages that we need, the next step is to look at API calls. Now consider that the adversary might want to write a payload like this. And this is your classic download a file from the web, then execute it, and try to cleanly exit the process payload. The problem is, when we're iterating over all the code pages in memory, what we usually find is something like this. We see a lot of just standard Windows function calls dealing with Windows, et cetera, and often these function calls we find while iterating over the code pages don't match up at all to what the adversary wants to actually use in their payload. So we need a way to actually find or look up those API calls. So as it turns out, something that is very common in almost all programs is dynamically loading both libraries and dynamically figuring out where function pointers are. And those are done with the API calls, standard Windows API calls, load library, and get proc address. And as it turns out, these are scattered throughout most code pages. So our solution, instead of actually looking for the API calls that the adversary really needs, we just look up the load library and get proc address calls, and then require that the adversary writes a payload where all of the API calls need to be dynamically looked up using the ROT payload itself. So the payload on the left would need to be rewritten to look like the payload on the right, and this is very similar to how our high-level language looks. Essentially, it's just loading a library to get the address of that library, then getting the address of the URL download to execute function, and then calling that function and continuing on. And here the @ symbol you're seeing simply represents the return value of the last function. Next, we've mapped out all these code pages. We found the API calls that we need, which were just those 2 API calls. The next step is to actually look for useful sequences of code that we can use as gadgets in the next step when we compile a payload. So the way we do that is by iterating over all the code pages we found, and we use the Galileo algorithm, originally introduced by Shikam in 2007. And all that algorithm does for us is give us an efficient way to extract all the short code sequences from all the pages of memory that we've found. Now, keep in mind that in the next step, we need a way to automatically use all these code sequences to compile a payload. So we need to abstract some of these code sequences into higher level gadget types, so we can work with them easily in the next step. So the way we do that is just by defining a few types, and each of these types just represents a discrete action, like moving a register into another register. And the way we map the code sequences to the types is by looking at the first instruction in any code sequence. For example, this first code sequence is just moving the register EAX into the register EBX, and that maps up exactly to a move register gadget. We also iterate through these, and if any of the instructions, the first instructions in the sequences doesn't map up to one of our gadget types, that's not useful to us, so we just get rid of it. Next, the first code sequence is actually just represented by one single instruction. So now, since there's no adverse effects that could possibly happen in subsequent instructions after that, we say that yes, this is a good gadget, let's take it, make it into a gadget, put it into our bin so we can use it later in our compilation phase. When we do have more than one instruction in a sequence, we need to examine all the subsequent instructions and make sure that they're not going to perform some action that's going to crash the program potentially. So if we look at this second instruction sequence with a pop EAX, that's simply loading a value into the EAX register, then we are moving the EAX register into the memory address pointed to by the ECX register, but we haven't previously defined ECX potentially. So this is something that could potentially write to an address that's not mapped into memory and could potentially crash the program. So we do our entire gadget analysis very conservatively, and for these situations, we just say we don't want to use that, we don't want to take the chance, and we discard that. Now in the last instruction sequence, the second instruction is just moving register EDX into EBX. It's not writing to a location in memory, and it's not killing the value that we just loaded into EAX. So we say that's okay, that's not going to cause any harm, so let's just add that into our gadget bin. The final step in all of this is taking the adversary's high-level exploit description and combining that with all the gadgets that we've actually found available in the pages we've iterated over, and trying to piece those together into a payload that's actually going to perform the actions that they want. So the way we do that is we look at each program statement and note that there's any number of ways that we could potentially combine all the gadgets that we've actually found to perform the actions in each of these lines. So what we do is generate all the possible gadget arrangements that could fulfill what's needed, and then we look at the gadgets that we have available. And we use algorithms similar to those used in the Q gadget compiler to do this. And this is something that was proposed by Schwartz et al. In 2011. Basically, at this point, we have all the potential ways to create our ROT payload, and we look at what we have available, and then we try to fulfill at least one arrangement of gadgets for each program statement. And when we're able to do that, we have a full ROT payload available now, and we can then serialize that into a form that the adversary can use. For example, if this is all running in a web browser as JavaScript, this would be serialized just down to a JavaScript string. Now keep in mind that everything I've presented so far is our initial implementation of JIT-ROP. And so there's a lot of room for improvement in this. For example, in our memory mapping phase, a lot of times when you're disassembling code, there's also a lot of data intermixed within that code. So we have there's the potential to misread data as code and accidentally point to a page that's not actually code and crash the program while we are mapping memory. So one thing we could do to improve this is have some better algorithms for discerning actual code from what's just data, but it's embedded in the code section. Another thing we could do is right now we just look at finding API calls. We haven't explored at all the direct use of system calls. So that's something that could potentially improve things as well. In the gadget finding phase, you notice probably that we're very, very conservative in the gadgets that we find. We throw out anything that could potentially have any adverse effects. So something we could do is lower that conservativeness, but that's going to be at the expense of complexity and adding a lot of code to ensure that nothing bad is going to happen. In the compilation phase, we've basically just defined a very small subset of all the ways that you can combine gadgets to achieve whatever actions the adversary wants to have. So another thing we could do to potentially reduce the total number of gadgets that we actually need to find is by defining just more composite gadgets that implement each operation. Finally, we could optimize this entire thing by improving the code throughout the entire framework. But even with all these things that we may do in the future, we can still show that our framework does pretty well. Now, one of the big questions is regarding page mapping. And since all of their steps in our framework rely on our ability to map out a large number of code pages, to find gadgets within them, to find API calls within them, it's worth looking at how well we're able to do that page mapping in detail. So one of the questions that comes up is, are there actually enough function pointers on the heap or the stack that we can leak in order to map out a significant chunk of the application's memory? So we sort of took the easy way out of this question, and we just assumed for all of our experiments that you only need to leak a single function pointer. And you'll see what we did in our experiments in a second. Second, once we have an initial page, we need to check if those code pages are actually interconnected enough, again, to see if we're able to map enough of the memory. And so the way we looked at this was we just tested this on a bunch of different applications that are popular and fun to exploit, represented by their icons there. So here's how we did our experiments. For each application, we opened that application just with a blank document, used standard Windows facilities to generate a memory snapshot of each of these applications. And that includes all the program code and data and where it's located at in memory. Then we built, instead of a JavaScript version of JIT-ROP, we built it into a x86, a native x86 version. And then we took as input to that program each of the memory snapshots and kicked off our entire process using a single code pointer. And then we repeated that for each application for every single code page there was. So we ran each one of these applications thousands of times. That's why we had to do it with a native x86 version. So here's some of the results of that experiment. What you're seeing here is a box plot for each application. The light blue color represents the upper quartile of the number of pages we're able to map out. The darker blue box represents the lower quartile of the number of pages, and the line in the middle is just the median. And keep in mind that for each one of these bars here, that represents thousands of runs where we kicked off the entire process from a different initial code pointer. So the way you can read this chart is that on average, over 50% of the time, regardless of where we started, we're actually able to map out about 300 pages or more of code memory. And it turns out prior work has shown that you really only need 10 to 20 pages of memory to build a payload. So this is good. So we continued on this experiment, and now we're looking at just one of the results for just one of the applications regarding API calls, and this is with Internet Explorer 10. And again, we have these box plots, and what we're showing here is how often we're able to find the load library and get proc address API calls. Remember, these are the only API calls that we need. Then we can actually just build a ROP payload that's going to use these API calls to look up all the other functions that will be needed in the payload. So again, now we find that on average, we're able to find between 9 to 12 of these API calls, regardless of where we start our initial mapping from. And we only need one of these in each category. And for the load library, we either need the ASCII version of that or the Unicode version. And again, the results here were similar for every application that we looked at. Now, the next step of our framework was to identify all the different gadget types and get as many of those as we could. So what you're seeing here in this box plot is a bar for each type of gadget that we defined, and it's showing the number of unique gadgets that we're able to find within that category. So you can see here that we find a good number of gadgets for every category except the stack pivot. It's kind of an important gadget. We only find just a very few of those on average. But right now, the way we define that is just simply as this one instruction, exchange EAX ESP. So it just swaps out the value of EAX for the value of the stack. And that could certainly be improved upon, but so far we haven't found really a need to do anything else with that, as you'll see later on in our demo. But the important thing here is that we usually find one or more of each type of gadget, regardless of the initial code pointer we use. I think it's also important to note here that we ran all of these experiments both with fine-grained ASLR enabled and without fine-grained ASLR enabled. The ASLR implementation we looked at was the most cutting-edge one we could find where the source code was available, and that's ORP by Pappas et al. From 2012. And the results are similar because we do the same thing whether there's fine-grained ASLR enabled or not. Our code page mapping works the exact same way. One interesting thing about this ORP implementation of fine-grained ASLR is that they actually include an extra step. They also do gadget elimination. So each time the application is run, ORP actually searches through the code and tries to identify gadgets that might be useful to an adversary and tweaks the code and changes it so that gadget no longer does what it was originally intended to do. And so one of the interesting things here is that that had no effect on the JIT-ROP framework at all because we're finding all of these gadgets dynamically each time the exploit is running. And what's kind of funny actually is after this gadget elimination, sometimes we actually found more gadgets than without gadget elimination. So next we ran end-to-end tests over a number of different exploit scenarios. So what you're seeing here in these bar graphs is just 4 different exploits and the number of seconds it took from the user browsing to the web page to the payload being generated and executed on their machine. So the first box here is actually a real exploit, CVE 2012-1876. And the target is against Windows 7 on Internet Explorer 8. And this vulnerability, we set up a memory disclosure similar to the one that Luca talked about earlier, where we overwrite the string size and then we're able to read from arbitrary addresses in memory. And we see that took about 22 seconds. So not so great, but not so bad either. Then the next 3 bars are showing different exploit scenarios where we have different types of memory disclosure vulnerabilities running under different environments. And all of these are artificial. They're just ones that we created to check the performance differences. So the second bar here is running the same type of exploit as the one that Luca described for the memory disclosure, but instead of running on IE8, we're now running in the Chrome V8 JavaScript engine. And so just by switching the JavaScript engine, it actually improved our performance double, or half the time. Next, we do the same exploit, but instead of Windows 7 and IE, we do Windows 8 and IE10. Again, this is an artificial exploit that we injected that is basically that same string overwrite vulnerability. And so we found just running in IE10 with its improved JavaScript engine, one of the biggest things that improved the performance here in terms of the differences in the JavaScript engine is the use of typed arrays in JavaScript. So with this exploit, we were able to run the entire process in just a few seconds, which is great. But then on the other hand, again running in IE10 on Windows 8, we did another type of memory disclosure exploit based on format strings. And you can see that's a lot slower at around 15 seconds. And the reason for that is because it takes a lot more to disclose a single byte of memory using a format string disclosure. Basically, every byte of memory we want to read, we have to allocate a number of strings in memory and go through all these format string functions as well. So you can see that, running under different environments, different JavaScript engines, and depending on the actual exploit that's used, the runtime really varies pretty significantly. But we feel this is pretty viable actually for real-world exploitation. So speaking of real-world exploitation, I want to get to probably the most enjoyable part of this talk, which is the live demo. And as Luca mentioned earlier, we are using CVE 2013-2551. And this is the same exploit that was used to win the Pwn2Own competition a month or 2 ago. And we're running this exploit on Windows 8, IE10, and so IE10 and Windows 8 is using basically the latest and greatest set of deployed defenses that are available right now. But at the same time, JIT-ROP is targeted to work against fine-grained ASLR, which is actually not implemented at all in IE10, Windows 8. So in this scenario, we're just generating a payload against standard ASLR. But the entire process should work exactly the same if fine-grained ASLR were employed. And so just to give credit where it's due here, I just want to make it clear that we did not discover this vulnerability. It's discovered by Nicholas Joly, and there was actually a Metasploit module written, I think, a few weeks ago by Juan Vasquez, and that Metasploit module works only in Windows 7 and IE 8. It doesn't work in Windows 8 because ASLR is enforced throughout all libraries in Windows 8, so there was no way to have a payload pre-written there. So let me just go straight over to the demo, and this is a live demo, and I'm hopeful that it will work. So first I'm just gonna, open up this web page, and the web page contains a little HTML plus some JavaScript. It also includes a library, which is the JITROP library in its JavaScript form. So let's open that up. And what you're seeing here is just a web page. It just has a single button. I'm going to press that button, and you're going to see some output in the debug console down here. And hopefully this will work. Sometimes it takes a few tries here to get the heap feng shuiing working correctly. Okay, so there we go. So what's happening right now is the memory disclosure vulnerability was used. It found a initial code pointer and provided that initial code pointer to the JITROP framework. So that's it. From there, the JITROP framework takes over and uses that initial pointer to try and map out as much memory as possible, to try and find all the gadgets that are going to be needed to build a payload, find all the API calls that are needed by the exploit description, and then it'll compile that payload and return it just as a JavaScript string. And this particular exploit takes about 20 seconds to run, as you saw. So let me just show you real quick, before I trigger the exploit, what kind of debug output we get here. So again, keep in mind, this is all running just as a JavaScript library. So what we get here is first an output of all the gadgets we found, organized by category. So we have no-op gadgets, jump gadgets, we have stack pivots. Now you saw earlier that one of the ones that we have the most trouble finding is this exchange instruction, but in this case we found 19 instances of it, so there's no problem here. We have pushes, we have things for moving values between registers, loading values into registers, some arithmetic gadgets, things for loading and storing into memory, arithmetic versions of those, and after all the gadget output, we're showing the API calls and how many of those we're able to find. And remember, we're just looking for get proc address and load library. In this case, we found 22 instances of get proc address on the pages that we iterated over. And we found only one instance of load library, and it's the Unicode version of that. Even though we found only one, that's all we need to build the payload. So after that, the payload has already been built. And this is just a textual representation of what that payload looks like. It's just listing all the gadgets out, and the values are loaded into various registers, etc., etc. So this particular payload, let me show you what we're actually trying to compile. Okay, so this is the actual exploit here, and this is what you as the adversary would need to provide for the JITROP framework. And it's just this high-level language, very simple high-level language, that's basically a sequence of API calls. In this case, we use load library to grab the address of kernel 32. Then we use get proc address with the result of that kernel 32 library location to grab the address of the winexec API call. And just call winexec. Remember, the @ symbol here is just the result of the last function. So in this case, the address of winexec. And we call it and give it a parameter to execute the Windows calculator. Then we want to keep things nice and tidy, so we look up the exit process call exit, and hopefully this will all run and execute calculator and cleanly exit. I can't guarantee it, but let's see. And there we go. And I have a few more payloads that I want to show you. Let me check how I'm doing on time. Okay, great. So I think I have time to do this. The other thing I want to show you is just running that same payload, but instead of redirecting execution to the payload, let's redirect execution to an address in memory that I know is going to be invalid ahead of time. So we're just going to redirect execution to the address of 1, which should be unmapped. Okay, let's go. Takes a couple tries here for the heap feng shuang. Okay, got it on the second try. So now again, we're just mapping out all the code pages that are available, finding all the gadgets, finding all the API calls that we need. And the reason I changed the address to 1 is in order to crash the program. And I want to crash the program because after that happens, I'm going to open it up in a debugger so you can actually see the ROP gadgets as they execute. So while this is running, it takes about 20 seconds or so. I can give you a little preview of some other payloads I'm going to show you. So this is just your standard does it work payload, a Windows calculator. The next one I want to show you after I go through this debugger is just to show you that we can do a lot more complex things with this very simple high-level language. And here I'm just chaining together a whole bunch of calls. I'm going to open a whole bunch of calculators. I'm also going to write some data to a file. Then I'm going to open up that data in Notepad so you can see that it was written. And then again, cleanly exit. Let's check on this here. Okay, so we're all done again. What I need to do is in the debug output, I'm outputting the address of our payload. But remember, we're going to redirect to an invalid address, so it should crash when I close this. Okay, it crashed, so let's open it up in the debugger. This is just a Munity debugger. And I hope you guys can read this when it comes up. It does take a second. Okay. All right, so let me just move this around a little bit so you can see it. Okay, so what you're seeing here is in this top left window is the current code that's being executed. In the right-hand window is the current value of some of the registers. And you can see in EAX is 1, which is what we put there. And on the bottom is the current values of what you see on the program stack. So what we're going to do is instead of redirecting execution to 001, I'm going to paste in here the address that I copied out of the debug output, say OK, and restart execution, but I'm going to single step into this so you can see the actual ROP gadgets in action. So I'm going to step into this call, and this call here is just a call into a virtual table function that we've replaced. Okay, so we've called into the very first address of our payload, and we can see that the code that it pointed to, which is a gadget, is that exchange EAX ESP. So this is your classic stack pivot to change the stack over to point to our entire ROP payload. So after this instruction executes, what you should see on the stack output down here is our entire ROP chain. Okay, so what you're seeing down here is just each address in our ROP chain, and the debugger is kind enough to point out where we're actually getting that gadget from. So you can see our code, using our code page traversal, we're actually getting gadgets from a pretty wide variety of different modules that are loaded into memory. And that's just because all these modules are interconnected in some way. So we get a gadget from the VGX DLL, GDI32, in TDLL, we get some from IE shims, and I could continue and go down this, but I won't. Instead, what I want to show you is just stepping through some of these gadgets so you can get an idea of what a ROP payload looks like as it's executing, and you can see how we constructed our ROP payload. So we just step through each of these, and all that's happening is each address, one by one, is popped off the stack, and each of the addresses points to some code sequence. That's our ROP gadget. And we continue on, and you can see values are being popped from the stack, and our ROP payload is being consumed. What's happening right now in the payload actually is a small preface to the actual payload that goes in and patches all the null bytes into the payload itself. Null bytes are something we had to get rid of for this particular exploit. So if I continued to step through this, you'd see the entire payload be consumed, and eventually Windows Calculator would pop up. But I'm not going to go all the way through that. It would take too long. So I'm going to close this, and I think I should probably wrap up soon. So maybe I'll skip this very large payload, and instead I want to jump to what would be what most real-world adversaries will be interested in doing, which is downloading a file from the internet and then executing it as a payload. So let me just change the payload that's going to be built and executed here to this download exec payload. And I got to remember to redirect execution to the correct place. Okay. That's that, and we can now run this. Okay, we got it on the first try here. And again, this is going to take about 20 seconds. JIT framework automatically mapping all the pages, gadgets, and APIs. So let me show you real quick what this payload actually is while it's mapping everything out. So again, we're just using load library and get proc address to dynamically find the address of the winexec call. And for winexec, we're just giving it the command to execute the command shell and telling the command shell to execute PowerShell, which in turn executes a small PowerShell program that downloads a file that I'm hosting right now on my own local host, because I don't trust you guys to actually connect to the internet, and then execute that file after we've downloaded it. So the goal is to download decafbad.exe. Okay, and we can see we've built the payload, we've returned it as this JavaScript string, and all that needs to happen now is we close the browser to trigger the actual redirection of execution. And with any luck, okay, we see PowerShell popped up. We didn't cleanly exit this particular example, so we got the crash message. But what happened is the file was downloaded from the internet. You can see it on the desktop down here, decafbad.exe, and it opened it up. And it looks like Microsoft Paint, but it's not Microsoft Paint actually. This is a program, this is a modified version of Microsoft Paint written by a colleague of mine, Nathan Otterness at UNC, called Caffeine Bad. And it just shows what happens when you have too much caffeine. Your drawing looks like this. So that's it for the demo. I'm just going to quickly conclude here. Basically, our goal was to try and see if fine-grained ASLR is actually providing anything that's beneficial above standard ASLR. And I think we've pretty clearly shown here that there is real no advantage to fine-grained ASLR. And a lot of people will suggest these quick fixes like, okay, it takes 20 seconds or so sometimes to generate a payload. Why not just re-randomize periodically? Well, we could do that, but to do it fast enough to where it's actually going to prevent this sort of attack, it turns out that the performance trade-off in doing that is just way too impractical. So what I think is that we need to move towards more comprehensive mitigations like for example, control flow integrity. And we need to not just look at these comprehensive mechanisms, but we also need to find practical solutions, so efficient solutions that don't take much runtime overhead to do. So personally, what I'm working towards and what Luca's working towards is more efficient, fine-grained control flow integrity and data flow integrity mechanisms. And so that's it. I think we'll take some questions now, if we have time.
We have 5 minutes.
Questions? Do you want to speak to ILR?
So it depends, of course, which kind of randomization you enforce. So the paper that we have read about re-randomizing periodically was also reshuffling and enforcing fine-grained randomization. And there the overhead was quite big, and they could only do it for a specific kernel. So I'm not aware of the work you are referring to, but the overhead should be quite high if you, in particular, if you want to re-randomize all the libraries that are included into your program.
Yeah, the techniques using software dynamic translation. So code basically being put in a code cache, and all software dynamic translators allow you to flush that
Yeah, that's definitely true. I mean, software dynamic translation is an option for re-randomizing, but as far as our experience have shown, software dynamic translation frameworks already add a lot of overhead to the application. So it's definitely a field that one needs to explore to make these things more efficient.
I think it's just a trade-off. I mean, if 10% is something you're willing to sacrifice for your web browsing, then maybe that's okay. More questions, please.
I think everyone is hungry for lunch.
Okay, well, thanks everybody.